Welcome to the Deep Dive. Today, we're cutting straight to the heart of PCI Express Generation 6. You know, PCIe Gen 6.
That's right.
You're here because you want to get smart, fast, without feeling buried in specs, and, well, that's what we aim to deliver.
Yep. For you, our listener, we've really dug into the details of the new PCIe Gen 6 specification. We want to pull out the essential bits and explain why this is, such a big deal.
Finding those aha moments, right?
Exactly. Uncovering those key advancements and what they actually mean in the real world.
Okay, let's jump right in then. The headline grabber has got to be the raw speed increase.
Oh, absolutely. It's quite remarkable, really. They've doubled the data transfer rate again. We're talking 64 gigatransfers per second per lane.
64 GTs per lane. Wow. What does that translate to in, like, a typical setup?
Well, think about a common by 16 slot, like for a graphics card or accelerator. That configuration can now hit a, well, frankly, mind-boggling 256 gigabytes per second of bidirectional bandwidth.
256 gigabytes. That's huge.
It is. And the key insight here isn't just the bigger number, it's the potential. It unlocks so much more throughput for demanding applications and, gives us headroom for future tech.
Okay, so beyond just faster is better, where will we actually see the difference? What improves because of this bandwidth?
Great question. Think about high-performance computing, HPC. Those massive simulations, they often get stuck waiting for data. PCIe Gen 6 helps smash through those bottlenecks.
Right, moving data between processors and memory faster.
Precisely. And then there's AI and machine learning. Training those huge models, like for image recognition or language processing, needs tons of data moved quickly. Gen 6 provides that fat pipe for faster training.
Makes sense. Those models are only getting bigger. What about data centers, the backbone of everything online?
Data centers are constantly pushing limits. Gen 6 is crucial for them. It supports the next wave of high-speed networking, think 400 gig Ethernet, maybe even faster down the line. Plus, super fast NVMe SSDs and those accelerator cards everyone's using now. This interconnect speed is vital for them to keep scaling up and stay efficient.
And what about things closer to home, like graphics cards or workstations?
Definitely. High-end graphics cards need immense bandwidth for, huge textures, complex scenes, real-time rendering. Gen 6 delivers that.
So smoother gaming and rendering.
Potentially, yes. And for professionals doing heavy video editing or 3D modeling, dealing with massive files, they should see fewer bottlenecks, much smoother workflows.
Okay, so speed doubled, clear benefits across the board.
Yep.
But how? How did they double it without just cranking the frequency way up? That usually causes problems, right? That's where PM4 comes in.
Exactly, you hit it. Instead of the old way, NRZ, which uses 2 voltage levels basically on or off, representing 1 bit, PM4 uses 4 distinct voltage levels.
4 levels instead of 2.
Right. And the key insight, the clever part, is that each level can now encode 2 bits of data in the same amount of time, the same clock cycle.
Ah, I see. So you're sending twice the data without doubling the actual signal frequency.
Precisely. Think of it like maybe like a delivery truck. It used to carry 1 package per trip. Now it can carry 2, but it's still driving at the same speed.
Okay, that's a neat trick. What are the immediate upsides of doing it that way?
Well, the big one is hitting that double data rate without the headaches of doubling the frequency. Higher frequencies mean more power draw, more signal integrity challenges, basically. It gets harder to keep the signal clean.
Right, more noise, more errors, potentially.
Yeah. So PM4 is a more, let's say, elegant way to boost bandwidth efficiency. And it's worth pointing out, this isn't like some experimental thing. PM4 is already battle-tested in other high-speed standards. Think Ethernet, InfiniBand.
Okay, so they're leveraging proven tech. Smart. Now, something else that sounds like a big shift is FLIT mode. What exactly is a FLIT, and why move away from the old variable size packets?
Yeah, FLIT mode is a really fundamental change. Previous PCIe generations used variable size packets, called TLPs, transaction layer packets. Gen 6 introduces the FLIT, or flow control unit.
Okay.
And the key thing is, a FLIT is a fixed size 256 bytes. And all the control information, like error checking codes, link management stuff, it's now bundled with these fixed size FLITs.
Fixed size. 256 bytes. What's the core advantage there? Why is fixed better than variable in this case?
Well, key insight is reduced overhead, especially when you're sending lots of small bits of data. When the control info is attached to a bigger fixed block, Less of the total bandwidth gets eaten up by that overhead.
Ah, so it's more efficient, especially for smaller transactions.
Exactly. More of the pipe is used for actual data. Plus, having these consistent fixed-size units makes life easier for the hardware inside the PCIe devices. Things like managing buffers, routing data, it all gets simpler.
Simpler hardware usually means faster processing, maybe lower latency too.
That's the idea. More predictable performance, potentially lower latency. It benefits all Gen 6 applications, really.
But are there specific things that gain more from FLIT mode?
Yes, definitely. Workloads with tons of small transactions, think some storage protocols, or even how different cores inside a complex chip might talk to each other. They really stand to benefit from that reduced overhead and the streamlined handling of FLITs.
Got it. Okay, so faster signals with PAM4, more efficient packaging with FLITs. But with all this speed, making sure the data arrives intact is pretty critical, right? That's where FEC comes in, forward error correction.
Precisely. You're pushing data so fast, and with PAM4's denser signaling, the chance of a random bit flipping an error goes up slightly. FEC is the safety net.
How does it work?
It adds a little bit of redundant information to the data stream. The key insight is this extra info allows the receiving device to not just detect, but actually correct minor errors on the fly.
Without having to ask the sender to resend the data.
Exactly. That's crucial. Resending takes time, hurts performance. FEC minimizes that. And the FEC in Gen 6 is designed to be lightweight, meaning it adds minimal delay itself.
So better data integrity, less waiting around for retransmissions. Sounds essential at these speeds.
It really is. It boosts reliability across the board.
Hmm.
It's especially helpful maybe over longer connections or in environments with more electrical noise where errors might be slightly more likely.
Makes sense. Reliability is key. Now, let's talk power. Being energy efficient is always a big goal. There's a new power state, L0P. Tell us about that.
Right, L0P. This is a clever power-saving feature. Basically, it lets a PCIe link dynamically scale down the number of active data lanes when it doesn't need the full bandwidth.
Oh, interesting. So like an by 16 link could temporarily run as by 8 or by 4 if there's not much data flowing.
Exactly that. If the device isn't pushing tons of data at that moment, it can throttle back the active lanes and save power. The key insight is dynamically scaling power consumption to match the actual workload.
That sounds really useful. What are the practical benefits?
Well, improved power efficiency is the big one. Less power draw means longer battery life in laptops, for example.
Definitely need that.
Right. And in data centers, it means lower electricity bills and less heat to deal with, which reduces cooling costs. It allows for much more granular power management.
And does switching between, say, by 16 and by 8 take a long time? Does it impact performance?
That's the clever bit. The transitions in and out of L0P are designed to be very fast, so the system can quickly ramp back up to full speed when the demand picks up without a noticeable performance hit. It's kind of a win-win.
Power saving without a performance penalty.
Nice.
Nice. Okay, let's switch gears a bit. Security, hugely important. Gen 6 adds CMA and IDE. Let's start with CMA component measurement and authentication. What's that about?
CMA tackles hardware integrity. It provides a way for the system's main firmware, like the BIOS or UEFI, to basically check the digital ID card of a PCIe device.
Check its ID card. How?
It measures the device's firmware and verifies a cryptographic signature. The key insight is establishing trust. You can verify that the firmware on, say, your network card hasn't been tampered with and that the card is genuine. It prevents rogue or malicious hardware.
Ah, okay. So it helps ensure the hardware itself is legitimate. How does IDE fit in? Integrity and data encryption.
IDE focuses on protecting the data as it travels across the PCIe. The key insight here is securing the communication channel itself.
Okay.
There are two main types. Link IDE encrypts data between two directly connected devices, like the CPU talking to an SSD. Selective IDE is more advanced. It provides end-to-end encryption even if the data goes through switches across multiple PCIe hops.
So CMA verifies the device, IDE protects the conversation. Where are these security features most critical? Who needs this most?
Oh, they're vital in many areas. Think security-sensitive environments, government, finance, healthcare. Data breaches there are catastrophic.
Absolutely.
Also crucial for cloud computing, protecting customer data in shared infrastructure. Edge computing, too, where devices might be physically less secure. And even things like autonomous vehicles or industrial control systems, where data integrity is paramount for safety and operation.
Yeah, you really can't compromise there. Okay, let's circle back to some tech details. You mentioned FLIT mode earlier. There are also enhanced encoding mechanisms within FLIT mode. What's the improvement there?
Right. So within FLIT mode, the way user data gets encoded for transmission is further optimized. The goal is to get closer to a direct 1 bit of data maps to 1 bit transmitted scenario.
Minimizing any extra bits added by the encoding itself.
Exactly. The key insight is maximizing the payload within each 256-byte FLIT. Previous generations sometimes had encoding schemes that added a bit more overhead. FLIT mode aims to strip that down.
So more efficient use of each FLIT, getting more actual data through. What's the benefit?
It just boosts overall efficiency and throughput. More of the signal is carrying your useful data. It can also potentially simplify the hardware design for the encoding, decoding logic in the controllers.
Efficiency everywhere. Okay, now managing all this data flow. There are updates to flow control. Shared and merged flow control credits? Sounds complex.
It sounds complex, but the idea is smarter resource management.
Huh.
Flow control stops a fast sender from flooding a slower receiver. Gen 6 makes this more flexible.
How so?
With shared flow control credits, different types of traffic using what are called virtual channels, or VCs, can borrow credits from a common pool instead of having strictly separate allowances.
More flexibility there.
Right. And merged flow control goes further, creating a shared buffer pool for certain common operations like memory writes and read completions. The key insight for both is better resource utilization and flexibility.
So the system can allocate buffers and credits more dynamically based on what's actually happening.
Precisely. It avoids situations where one channel is starved while another has spare capacity. This leads to more efficient hardware use and can potentially reduce latency by smoothing out the traffic flow. It's particularly helpful in complex systems like servers or networking gear that use lots of VCs and handle heavy I/O.
Smarter traffic management. Got it. Now, something else added in FLIT mode, segment numbers and TLP headers. Why add that?
Yes, the hierarchy ID or segment number. This is important for more complex PCIe setups. Imagine systems with multiple main CPU complexes or lots of switches creating different segments of the PCIe fabric.
Okay, like different zones in the system.
Sort of, yes. This segment number in the packet header basically tells the hardware which zone the packet needs to go to or came from. The key insight is enabling more efficient peer-to-peer communication between these segments.
So devices in different zones can talk more directly without maybe going all the way back up to the main CPU?
Exactly. It simplifies routing for that peer-to-peer traffic. It takes load off the central root complex and really helps scale up these large, intricate PCIe topologies. Think high-end servers, HPC clusters, big AI training rigs.
Makes perfect sense for those complex beasts. Okay, nearly there. Lastly, the new link-level functionality specifically for FLIT mode. What fundamental improvements are happening at this really low level?
This is about refining the very basic language of PCIe communication when using FLITs. The packet headers themselves are redesigned. The key insight is making them cleaner and more efficient for the hardware to process.
How are they cleaner?
Well, they have larger fields for things like transaction tags, which lets the system track many more operations happening concurrently. We already mentioned the explicit segment numbers for easier routing. Also, the field that indicates the type of packet is now fully decoded, meaning its value consistently tells the hardware exactly what kind of packet it is, simplifying routing decisions again.
So bigger address books for tracking things, clearer signposting for routing. It sounds like foundational plumbing upgrades?
That's a good way to put it. These link-level changes benefit everything built on top. They lead to better link efficiency, better scalability, potentially better performance because you can track more things at once, and maybe even simpler hardware design. It's refining the bedrock of Gen 6 communication.
Well, that was definitely a deep dive. Let's try to wrap it up. To summarize the big hitters, PCIe Gen 6 gives us that massive bandwidth jump, right? Doubled speed.
Yep, 64 GTs per lane, up to 256 gigabits on my 16.
And it achieves this smartly, using PM4 signaling. Then there's much better efficiency with the shift to fixed-size FLITs.
Right, reducing overhead and simplifying things.
Plus, we get crucial reliability with forward error correction, smarter power saving with the L0P state,
Absolutely.
and really significant security upgrades with CMA to verify hardware and IDE to encrypt the data itself.
Those are the key pillars, absolutely. And it's vital to connect these back to the impact. These aren't just numbers on a spec sheet.
Right.
They enable the next generation of HPC. They fuel faster AML development. They make data centers more powerful and efficient, push graphics forward, empower creative professionals. It's foundational.
It really makes you think, doesn't it? With this much more capability in how system components talk to each other, what entirely new things become possible? What applications that seem science fiction today might this unlock?
That's the million-dollar question, isn't it? What bottlenecks that we currently just accept might Gen 6 completely obliterate?
Fascinating stuff to consider. Thanks for taking this deep dive with us today.